Introductory circuit analysis using an unconventional, intuitive, approach. Greetings viewers. Here we emphasize how things really work intuitively rather than blindly use mathematical methods.
This is the first session of a series of videos teaching circuit analysis using an intuitive approach. Let us consider the simple RC circuit shown. To solve even such a simple circuit, the conventional approach is to first create a differential, or an integro-differential equation. A linear, ordinary differential equation can be solved as a sum of complementary function and particular integral. Alternatively, we could use operational calculus, that is Laplace transform, to solve both differential and integro-differential equations. Whatever be the method, a certain mathematical background is necessary for arriving at such analytic solutions. The method we present here does not assume such a mathematical background. All we need is basic calculus and working knowledge with spreadsheets such as Microsoft Excel. And as you will see, this method gives you a better insight into the internal working of the circuit compared to the analytic methods. To analyze such a circuit, we will attempt to find a numerical solution using easily available and ubiquitous spreadsheet tool. You may discover similarities between this method and simulation tools used in real-life engineering. However, here you are in total control of how you set up your very own simulator. The principle is to find the various parameters such as voltage, current using KCL and KVL. Then we find time derivatives of these parameters as required. This allows us to calculate the parameters at the next instant. This can be repeated on and on. Therefore, this is an iterative method. For the specific RC circuit under discussion, let's say we know the current at an instant t. We calculate the charge deposited on the capacitor due to current flowing for very small duration delta t. As a result, the small voltage change across capacitor can be calculated. Now we can recalculate the current at an instant t plus delta t. This is repeated on and on. Here is a guideline to the selection of delta t. The rule of thumb is to make delta t at least an order of magnitude smaller than the time constant of the circuit. For complex circuits, time constant may be difficult to assess. For such cases, we try to estimate bandwidth from which time constant can be determined. Now we demonstrate the process using a spreadsheet, which is Microsoft Excel in this case. We start with a step function stimulus to the RC circuit. For simplicity, we assume that the capacitor has no charge to start with. That is, initial voltage across capacitor is 0. We will remove this restriction later. We will now enter in the spreadsheet the values of C, R, delta T, and initial voltage across capacitor. Value of C in picofarads is entered. Value of R in kiloohms is entered. Time constant is calculated as the product of R and C and expressed in microseconds. Value of delta T, that is time step, is entered in microseconds. Initial voltage across capacitor is entered. Here is a summary of parameters entered. Next goal is to generate the stimulus, which will be a step function to start with. A conceptual description of the step function is given in the lower half of the slide. Before we generate the stimulus, we will discuss timing convention, and ideal switch characteristics in next couple of slides. Switch is closed at t equals 0. Before closing the switch, the capacitor might have stored charge and therefore a voltage. This is the initial condition. We define t equals 0 plus the instant immediately after closing the switch. This is valid for an ideal switch. More details in next slide. We assume the switch to be ideal, that is, it operates instantaneously. Also, it has zero resistance when on. Column A represents time, with increments in steps of delta t, which is 0.01 microseconds in this case. Switch is closed at t equals 0, represented by cell A7. We will enter the stimulus in column B. It will be a step function for the moment. The switch gets closed at t equals 0, when the stimulus is 0. Beyond this, the stimulus assumes a value equal to the amplitude of the step function, which is arbitrarily selected to be 1 volt. The rise time of the step is therefore delta t, unlike an ideal step where it is 0. The stimulus is plotted as shown. We just entered the step function stimulus. Next we will enter the formulas for the various variables as shown. Let us now identify the variables. Column E is reserved for voltage across capacitor. Column F is reserved for voltage across resistor. Column G is reserved for current. Column H is reserved for rate of change of current, expressed in milliamps per microseconds. Column I is reserved for current after delta t. We have identified and entered the variables. Now let us enter the initial conditions for each variable. In this particular example, the initial voltage across capacitor has already been entered as 0. Initial current is 0 since switch is open. As a result, rate of change of current is also 0. Initial voltage across the capacitor should be equal to value entered earlier. Initial current is 0 as switch is open. Initial voltage across the resistor is 0 since initial current is 0. Initial value for rate of change of current is 0 since current has been 0 all along. Current at t plus delta t is 0 since both initial current, as well as rate of change of current are 0. Next we enter formulas for the variables at t equals 0 plus, that is just after switch is closed. Voltage across capacitor cannot change instantaneously, therefore it must be same as the initial condition. From KVL, stimulus voltage is equal to sum of resistor and capacitor voltages. Therefore, voltage across resistor is obtained by subtracting capacitor voltage from stimulus. Current is obtained by dividing resistor voltage by value of the resistor. Time derivative of current is obtained by taking the difference of present value of current and previous value of current, then dividing by delta t. Current at next instant of time is calculated by using Taylor series and neglecting higher order terms. Now we consider the formulas for t greater than 0 plus. For t equals 0 plus, the capacitor voltage was set at initial voltage, as voltage across capacitor cannot change instantaneously. However, for t greater than 0 plus, current has already started flowing and depositing charge on the capacitor. As a result, voltage across capacitor will change. The charge deposited over time delta t is current times delta t. We use the value of current calculated at time t plus delta t for this purpose. Dividing the above incremental charge by capacitance, we get the incremental change in voltage. We add the incremental voltage with the previous value of voltage to get the current voltage. Other formulas stay the same as for t equals 0 plus. Let's see what has happened at t equals delta t. The voltage across the capacitor is still 0 but current is flowing. Please refer to the plot. Let's calculate variables for few more time samples. This is easily done by dragging the mouse. Watch how current and capacitor voltage changes in the plot in the next slide as we drag the mouse. We have calculated few time samples by dragging the mouse. For better clarity, we are showing the plot separately. Please note that neither the capacitor voltage, nor the current changes linearly. Why the deviation from linearity we saw in the previous plot? Charging current decreases due to increase in capacitor voltage as the stimulus is fixed, but capacitor voltage still keeps increasing. That reduces charging current even further, thereby further reducing rate of increase of capacitor voltage. In other words, KVL creates a feedback mechanism that prevents linear increase of capacitor voltage. What if we keep increasing the stimulus continuously? We will address this in session 2. Theoretically, infinite time is required for the capacitor to charge completely and reach the steady-state value. In reality, 95% of steady-state value is reached in mere 3 time constants. 99% of steady-state value is reached in 5 time constants. Even in just 1 time constant, 63% of the steady-state value is reached. Please refer to the table shown. You are encouraged to investigate the effect of changing the time constant. Now we ask ourselves the question, how accurate is this numerical method? To verify it, we will compare results with that obtained from analytic methods. Here is a plot of the capacitor voltage obtained by the present method, overlaid on that obtained from formula in the previous slide obtained analytically. The one obtained analytically is named the RVC and drawn with dotted lines. Visually, the agreement between the present method and analytic means look excellent. Let us now determine quantitatively how good the agreement is. For that we will calculate the percentage error between the present method and the analytic method for each time sample. Percentage error is calculated for each time sample. We observe the following. Barring first few samples required for converging the solution, maximum error barely exceeds 0.5% over the entire time record, not shown. Making delta t smaller reduces the error further. For example, delta t equals 0.007 microseconds reduces maximum error from 0.5% to 0.4%. You are encouraged to investigate error for current as well as effect of delta t on error. What happens to the error when there is a zero crossing present, such as if initial voltage across the capacitor is negative? So far, for simplicity, we assumed the initial voltage across the capacitor to be zero. We now remove that restriction. We consider 2 cases of initial capacitor voltage, negative in the left side plot, and positive in the right-hand one. You are encouraged to find the answers to the following. For positive initial capacitor voltage, why immediately after closing the switch, the current is negative? In which case the capacitor charges faster, for initial voltage positive or negative. What happens if initial capacitor voltage is exactly equal to the amplitude of the step function? At the end of the video, we will discuss pulse excitation. Generating a pulse is self-explanatory. We have to keep in mind that we cannot generate an ideal pulse using this technique, that is, a pulse with zero rise and fall times. The minimum value of rise and fall times is given by delta t. Pulse stimulus in column B. Start of pulse. End of pulse. Example of a pulse with duration less than the circuit time constant. Example of a pulse with duration significantly greater than the circuit time constant. The current approximately resembles a differentiated version of the pulse. Voltage across the capacitor resembles integrated version of the pulse. Voltage across the resistor resembles differentiated version of the pulse. Integrated and differentiated waveforms. You can create any arbitrary stimulus waveform with this method. The process may become too complicated with analytic method.
This concludes the first video on RC circuits. Thanks for a patient hearing. We plan to come up with more exciting videos on other circuits. Please feel free to comment or email if you have questions, comments, or need benchmark spreadsheet files. Till then, stay safe, and stay tuned.